As a continuation of our conversation on Bode plots, let's consider the following compound transfer function. If you look, it contains two different components in the denominator. We have j omega over 1,000 plus 1 and j omega over 100,000 plus 1. Now, if we were dealing with individual transfer functions, if I had broken this up into a product of h1 and h2, we would know how to plot h1 and h2 pretty simply. Okay, so let's say that h1 is 1 over j omega over 1,000 plus 1, and h2 is 1 over j omega over 100k plus 1. If I were doing those Bode plots, I would know how to do each of them separately. Okay, we already learned how to do that in the previous video. So this one would have been a gain of 0 and then 20 decibels per decade. Okay, with the cutoff frequency happening at 1,000, and this would be a slope of minus 20 dB per decade, and that's 0. And the other one would be exactly the same. The only thing that would be any different would be the cutoff frequency. So putting it all together, we'd see that again we have a gain of 0, and then it rolls off again at minus 20 dB per decade. The only difference being is that now instead of this being 1,000, this is going to be 100k rads per second. Okay, but this is still 0 dB, and this is still minus 20 dB per decade. So the question now is, what happens when you put them both together? Okay, I want to know what happens when I have a compound transfer function that is their product. And happily, decibels gives me yet another benefit, and here's the benefit. If you remember from studying logarithms in pre-calc or wherever you learn it, if we take the log of AB, that should be equal to the log of A plus the log of B. So look what that affords us. We remember that decibels is a log plot. So in other words, if I take decibels of h1 and h2, because decibels is a log, then really what that tells me is I need to do decibels of h1 plus decibels of h2. So in other words, the Bode plot of this compound transfer function will really just be the sum of the two individual Bode plots. So let's go ahead and put that sum together. Doesn't get much easier than a sum. So this is going to be log of omega. This is going to be dB. And at low frequencies, I'm adding a constant of 0 and a constant of 0. And that's going to give me 0. And then when I get to 1,000 rads per second, once I get to 1,000 rads per second, h1 will contribute a slope of negative 20 dB per decade, and h2 will contribute a constant of 0. So 0 plus negative 20 will give me negative 20 dB per decade. Okay, and that will happen, that breakpoint will happen at 1,000 rads per second. And then when I get to 100,000 rads per second, I'll be adding a slope of minus 20 dB to a slope of minus 20 dB, and that will give me now a slope that's twice as steep as before. That will now give me a slope of minus 40 dB per decade. Okay, so in this case, this happened to be 100k, and this is 0 dB. This is minus 20 dB per decade, and this will be minus 40 dB per decade. See how clean that is? All right, and then for even more fun, you could see that between 1,000 and 100k, there's actually 2 decades. So one decade would get you from 1,000 to 10,000, and then another decade would get you from 10,000 to 100,000. So from here to here, there's 2 decades, which means that 2 decades at 20 decibels per decade means that you should have gone down by, this point should be about minus 40 dB, okay? Which is a gain of 0.01. So once again, the Bode plot lets us make some pretty nice observations pretty easily. The only other thing I want to add to the conversation about Bode plots is what happens when you have a j omega term in the numerator. And when you have a j omega term in the numerator, instead of decreasing your slope by 20 dB per decade, it makes your slope increase by 20 dB per decade. And we'll see more examples of that later on in the lecture series.